Welcome to Dr. Jed's Calculus videos. This is the second part of section 5.2 of Rogowski. So we're talking about signed area. So it's a continuation of what we did before, but instead of using the rectangles, we'll just talk about ways of calculating area from rules. Give some examples, more rules, more examples. So let's start right to it. It's not that much work, but it's better if we look at it carefully. So we're going to use this notation. The integral from a to b of f of x dx. Maybe I should write that out. The integral, that's a g, from a to b of f of x dx it's the signed area. Now, signed area means if it goes below the x-axis, we count it as negative area. In real terms, negative area doesn't make sense. It's like antimatter, except antimatter exists in negative area, not so much. But for our purposes, sometimes we need negatives. In this example right here, there are no negatives, so we don't have to worry about it. What is the integral from 0 to 5 of f of x dx? Well, that means I want the area. And in this particular case, we can find it out exactly. We don't need right rectangles, left rectangles, or the RFPC thing, or any of that. Because, well, how do you do this? Well, you look at that, what is that shape? It's a trapezoid. So we could just use a trapezoid rule. Or you could break it into pieces you know. If I break it into this piece, what's that? It's a triangle. Triangle with a width of 2 and a height of 2. The area of a triangle is 1/2 base times height. So 1/2, 2 times 2 is 2. And then over here, we have a rectangle of a height 2 everywhere. So this is like a constant function in there. Height 2, width of 3. So there's a total of 6. So the area under this curve, all of this, is exactly 8. That's not an approximation, that's an exactness, if that's a word. Well, in any case, that is the area. Now, sometimes you don't have the luxury of an easy function, but there are ways in which we can make it work better. Here are some rules. So the first rule, if it's constant on the top, it's just a rectangle. So it's the height, which is the number, times the width, which is top minus bottom, b minus a. So if we're just taking the integral from a to b of, say, 5 dx, it would be 5 times b minus a. Along the same lines, if it's an x, well, we're going to have a trapezoid. And you can use the trapezoid rule. It's the average of the heights on each side, which is b plus a over 2, times the width, which is b minus a. If you multiply all that out, you get 1/2 b squared minus 1/2 a squared. We'll do an example of this to show how it works. But more importantly, perhaps right now, is these two. These two properties make the integral what's called linear, which is to say, just like the derivative. If you had a number, you could pull the number out before you took the derivative. If you added or subtracted, you could split them apart and take the derivative. Same with integrals. The integral from a to b of a number times a function dx, you pull the number out, and then you've got this. Or the integral from a to b of f of x plus or minus g of x dx, we can break this into an f integral and a g integral, and just keep the plus or minus in between. There's lots of rules, there are more to come, but let's do an example of these rules. So in this example, the integral from 1 to 4 of f of x dx is 7.1, whereas the integral from 1 to 4 of g of x dx is 2.5. So, what's the integral from 1 to 4 of f of x minus 2gx dx? Well, the rule said we can split apart in a minus sign. So I'm going to do that. All I did is separate into 2 pieces. Now the other rule that I'm going to be using here, there's a 2 here. I can pull that out. So I'm actually going to do that right away without writing another step. And then this one is known, it's 7.1. That one's known, it's 2.5. So this is 7.1 minus twice 2.5. That's not a lot of work to do. It's 2.1 all told. Now another one, for a more specific function. What's the integral from 1 to 4 of 5 plus 2x dx? Well, we can split the plus, and we can pull the 2 out. Let me do that. So, this is a constant. We had a rule for that. It's going to be the constant 5 times the width. 5 times 4 minus 1. Plus, there's the 2, so I'll keep that. And this, the integral from a to b of x dx was 1/2 of b squared minus 1/2 of a squared. So it's 1/2 of, I'm sorry, 1/2, not 1/4. 1/2 of b squared minus 1/2 of a squared. That's kind of messy, but notice the 2 very conveniently. 2 times 1/2 cancels, 2 times 1/2 cancels. This is just 4 squared minus 1 squared. 4 squared is 16. Minus 1 squared is 1, so that's 15 total, counting that in there. This also is 15. It's coincidence. I don't know why it's always 15s. But the total is 30 for this integral. What happens if we put an x squared in here? Well, right now we don't know. But those two, just from geometry, we can do. Rectangles, trapezoids. Now, in addition to adding and subtracting and multiplying by constants, integrals are also areas. So, in a real sense, if we take the area from a to b and add it to the area from b to c, we should get the whole area from a to c. So how does that work? If we're going to take the area from a to b and then add the area from a to c, we've got the whole area from a to c. That's what this says. Now you can flip this all around. And also think about this. If you've got the area from A to A, how much area do you have? You have no width. Sure, whatever height you have, but you have no width. So the area from A to A is 0. And then if I'm tricky, and I put this as A to A, make that an A here, I can solve backwards for the integral if B and A are reversed. The only way to make this work, so the area from A to B is that, but if I go from B to A, I'm going backwards. And the order of these makes a difference in the form of a plus or minus sign. The integral from B to A of f of x dx is minus the integral from A to B of f of x dx. That may not completely sit well with you right now, but this dx is telling you we're moving little dx's in this direction. If we start small and get big, it's happy. But if you start big and get small, it has to go in the negative direction. And that's where that negative comes from. Not from this part right here, but from this part right here. Anyway, let's take a look at these rules, plus one more. This is called the comparison theorem. It's a fairly obvious concept, but if you've got a function that's smaller than another function, so f is always smaller than g on this interval, then the amount of area you get if you integrate from a to b of f of x dx has to be less than the amount of area you get from a to b of g of x dx, or at least less than or equal to. G is bigger, so the amount of area you get is more. Now, what does this all tell us? So here's a more complicated example. So I'm going to use the same one as before. The integral from 1 to 4 of f of x dx is 7.1. And now I'm going to tell you from 1 to 2 of f of x dx is 4.4. I'll use both of those pieces of information, and I'm going to tell you that g of x is bigger than or equal to f of x on the whole interval. So what can we tell about g of x integrated from 2 to 4? Well, we know it's bigger, so we're probably going to use this. But to go from 2 to 4, we need to know about the other function too. I've drawn a number line here. We know the area from 1 to 4 of f of x dx is 7.1. So all of this for f is 7.1. We know the integral from 1 to 2 of f of x dx is 4.4. From 1 to 2. There's a 4.4 amount of area here. So what does that tell us about the integral of f of x from 2 to 4? It's going to be the whole distance minus the smaller piece. So that is 2.7. Is that right? Yep, that's right. Now, how does that help us for G? Well, G is always bigger than F on the whole interval. So that means that G is always bigger than F on the whole interval. The integral of G is bigger than the integral of F. And we know what the integral of F from 2 to 4 is. So this is bigger than or equal to 2.7. This may seem like fairly basic things, and if it does, that's great because you're really mastering it. Or it may seem actually pretty hard, in which case that's reasonable too. If you practice this enough, it will make a lot of sense. And today in class we'll practice. Until next time, this is Dr. Jed.